You can get back to your desks. All right, so here we go. All right, so the first question, limit as x approaches -2 from the left-hand side. From the left-hand side, right? So here's -2 approaching from the left. What do we get? Well, I mean, the answer's there, but right? Coming in like this, approaching 2. Approaching -2 from the right-hand side, you're approaching 1. Part C, what is the limit as x approaches 0? So it does not exist because from here's 0, so from the left you're headed there, from the right you're headed here, different places. Does not exist. Number 7, what's f of 0? Well, f of 0 is wherever, wherever you have a solid dot at 0, and that's 3. All right, E, the limit as x approaches 2. Now it doesn't say plus or minus here, right? Which means you have to check from both sides. And as you approach 2, from the left and from the right, it approaches 1. Good? And then here, as we approach 3 from the right, oh wait, did I miss one? Oh, I missed one. Sorry, when we approach 3 from the left, so here's 3 as we approach from the left, the function is taking off up to infinity. And then as we approach 3 from the right, it's kind of hard to see it, but it's coming down like this. It's approaching -2. It's this. And then lastly, what's f of 3? And if you go to 3, you can see there's an open circle here. This is an asymptote, so it's undefined. Okay, that was the first page. Second page, yes?
I have a question. F, doesn't it have to be marked?
Yes.
Where? What do you mean?
Like,
For which one are you talking about?
F.
Oh, sorry, I thought you meant f like the function f. Sorry.
No, no.
What do you mean it has to be marked?
Like, doesn't it have to be like defined?
Nope. We're approaching 3 from the left, right? That's what this means. We're trying to let our x values approach 3 from the left-hand side. We're saying, what does our function do?
Oh, okay.
So here's 3. As we approach from the left, our function is doing what? As we get closer and closer to 3 from the left, I go up and up and up and up and up, keep going forever. So the arrow implies that that's a vertical asymptote. Understand?
Yeah.
Okay. All right, so on number 2, you get 0 over 0. And I have roots here. So roots, you should be thinking conjugate. So you come in here with the conjugate on the top and the bottom. When you multiply out the top, you get x minus 3. And then on the bottom, you have to factor this as a difference of 2 squares. I did one very similar to this in class. And then this cancel, and you're left with a 1 on top. You're left with the factor x plus 3, and you're left with this. And then you just plug 3 in, and you get this. And that's that. Okay, so conjugate. Yes?
I did it a different way, but I had the same answer.
That's okay, as long as your algebra makes sense. Yeah. Okay, and then on this one, I actually, when I did the solution, I realized that I did it for approaching 5 from the left. This is from the right, so my work is actually not correct here. I'm supposed to approach from this side, so I'm supposed to be approaching with numbers like -4.9. And then when you take those numbers and you plug them in here, you get little tiny positive numbers, not negative numbers. And so the answer should be positive infinity, not negative infinity. And then the last one, oh, and I should say that the reason I did it this way is because I got fixed over 0. Fixed over 0, your answer is either infinity or negative infinity. You have to go figure out which one it is. That we did last class, right? And then this one was the one with that special formula that we have to have memorized, where we have sine of junk over junk, right? So you realize you get 0 over 0 here. You split this up into sine 5x over 1 and then 1 over sine 7x. and then you start to play that game. You have to figure out, it'd be really nice to have 5x here, so you introduce 5x over 5x. When you do that, things are great, but then you realize here you need to have a 7x, so you pull the x from here, and then you introduce the 7 over 7, slide the 7 over there, and I'm going quickly through this, all right? So you get this expression, this goes to 1, 1, 5, and 1 7, so you get 5 sevenths. All right, so that's, I know a lot of you are like, wanted to know if you did it right, so here we go. That's the key. I will, I'll grade those and get them back to you. So that's your first quiz. What do you think? Yeah.
So, do we get partial? Like, I just messed up a little bit.
Yes, I will get partial credit as long as I can determine what you're doing. Yeah, as long as your work makes sense. But on the other hand, if you got 5 sevenths on that last one, but you don't have any work, then you don't get credit. You can't just get the answer. Yeah, I mean, yeah. I have to see something other than just 5 sevenths. All right, we're moving on. So the reason I don't like giving quizzes, I would love to give a quiz every day because that would keep you honest with your work, all right? But the reason I don't like to is that just ate 25 minutes of class, and we just don't have time for that. But, expect a quiz every day. Expect it every day because I can give you a quiz any day. Also, sometimes I will allow you to use your homework. Just this one I didn't. Okay. All right, so we're moving on. Last time, what we talked about were, what happens when you take a limit and you get fixed over 0. And we said, well, that's where we're going to have some sort of asymptote, right? Now we switch gears, we do something slightly different, and maybe I should. So this is what we talked about last time. Infinite limits. As opposed to today, we are going to be talking about limits at infinity, right? So don't confuse these with infinite limits. So everything we've done up to this point, right? Every limit that we've looked at, we've always let x go to a number, right? Like x is going to 2, or x is going to 5 from the left, or this has always been a number, hasn't it? Now what we're going to do is we're going to replace that number with either infinity or negative infinity. So we're going to let x approach infinity or x approach negative infinity. And these, anytime we see these are called limits at infinity. And the idea behind this is this. You have some function. So in this particular case, I'm using the function f of x equals 1 over x. And what we're asking ourselves here is what is the limit as x goes to infinity? So what is the limit here as x goes to infinity of this function 1 over x? That's the question. So that's not a number anymore, right? Infinity is an idea. So essentially, we're imagining that we're going to let our x value, right, this is our x value, approach positive infinity, which is down the x-axis this direction to the right forever, right? Just keeps going. And the question is, does the function do something as I head that way? So let's look at what happens. So I have a dot there. See my little dot? It's going to start moving to the right. Sorry, that it's hard to read that f of x thing, but can you tell it's getting smaller? The function is getting smaller, isn't it? Now I'm going to zoom in on it so we can follow it. And now I'm just going to kind of notice my x values here, right? Now I'm at 8. The value of the function there is 0.125, right? As I move to the right, what happens? It gets smaller and smaller and smaller and smaller and smaller and smaller. That number is getting smaller. What is that? What is the function approaching? 0, right? It's getting smaller and smaller and smaller. So this limit should be 0. Understand? Now, if we look at the function itself and just think about what's happening, I think it's easier to see why it's 0. On the top, you have the number 1, right? Yes. And on the bottom, you have a denominator that's getting bigger or smaller. The denominator is getting bigger, right? So if you take a fraction, like let's say we take the fraction 1/2, that's bigger than 1/3, right? Like if I let the bottom get bigger, the fraction gets smaller? So if that's bigger than 1/4, and that's bigger than 1/5. So what's happening is like as I let the denominator get bigger, as long as I leave the numerator alone, right? As long as I leave it as 1, as the bottom gets big, the fractions get smaller. Yes? So that's what I want you to take away from this first example here, is that if your numerator is fixed, right, like 1, and your denominator goes to infinity, the function goes to 0, right? Okay, and I believe on that table I gave you from last class that had the summary of the limits, right, this thing right here, do you see the bottom right-hand corner? Do you see where it says fixed over infinity is 0? Anytime we have fixed over infinity, we have the limit goes to 0. Okay? What do you mean, negative infinity on the bottom?
Yeah.
Good question. What if it was negative infinity? So would that change our answer? So let me change this. What if I change this limit to the limit as x goes to negative infinity of 1 over x? Here's the picture, right? What would happen here? If I go to negative infinity, I'm no longer going out to the right, correct? I'm going out to the left this time. But look at these values, right? You go out, let's say, to -1, you're down here, right? That's a negative number. And then I go out a little further, it's still negative, right? But it's smaller. And then all of these numbers out here are getting smaller and smaller and smaller. Now they're negative, right? But what are they approaching? They're still approaching 0, all right? So as long as the top is fixed, it actually doesn't matter whether or not that's positive or negative. That makes no difference for this. And then same thing down here. If this is infinite, it doesn't matter if it's positive or negative. No matter what, this is headed towards 0. Okay? Now, it does not work this way if that's 0 down here, right? Like if it's fixed over 0, then it could be positive and negative, and that's what we have to go determine. But if it's fixed, doesn't matter if it's positive or negative on top. The bottom's getting huge, doesn't matter if it's positive or negative. That ratio tends to go to 0. So I'm answering your question on the next part of the note. I go out to the left, same thing, right? Goes to 0. All right, so here's an important property that we should memorize, and that is anytime we see 1 over x to any power. So like we just did 1 over x to the first power, didn't we? Like 1 over x is the same as 1 over x to the 1. If we see 1 over x squared, 1 over x cubed, 1 over x to the 4th, any power function down here, as long as the power on the x is a positive number, then those limits go to 0. And you can see here, here's 1 over x, right? So just by looking out the right-hand side, we already know that went to 0 and the left-hand went to 0. If I change that to 1 over x squared, that's what 1 over x squared looks like. That's that volcano function. That's 1 over x squared that we're looking at right there. And can you tell still, go out to the right, heads to 0, go out to the left, heads to 0. And this will hold for any positive integer. If I do 1 over x cubed, that's what it looks like. Looks a lot like 1 over x, doesn't it? But same thing, it tapers off to 0 on the left and on the right. 10th power, there's 10th power. All right, so now let's do this example here. Yes?
Is the power, does it have to be a whole number or can it be a fraction?
Good question. The question was, what if you have this, 1 over the square root of x, right? That's not a whole number power, right? That's x to the 1/2. This will still, in this particular case, if we went to infinity, x is going to infinity, you have a fixed number on top, right? And on the bottom, the radicand, the thing in here is getting big, right? So you're really doing like the square root of an infinitely large number. That's still an infinitely large number, isn't it? So this would still go to infinity, and so you'd still get 0. Now, the note that I just put up said it only holds for integers, but we will see in a little bit that it holds for this too. You just can't have negatives down there. Why does it not work with negatives? What if I have x to negative 1? Why does that not? Why is this limit as x goes to infinity, why is that not 0? Because what does this really mean? What does x to negative 1 down in the denominator really mean? Yeah, this is really 1 over x, isn't it? And then you could just flip that fraction. So this is really what? Just x. And now what happens to x as x goes to infinity? This gets huge, right? So the answer to that is infinity, not 0. Does that make sense? If you have negative powers down on the bottom, then they really flip back up and then they become huge. All right, let's take a look at this one. I'm going to write it down. Limit x goes to infinity, 3x squared plus 2x minus 5 over negative 4x squared plus 7. Okay, let's do that. All right. Franklin. Where's Franklin? Franklin? Have the right class here? No. Okay. How about Michael? Michael Sanchez. Okay. Michael, what's the first thing we always do when we're doing a limit?
Check to see that it's not 0 over 0.
Yeah, we just check to see, like we just plug a number in, right? Just plug the number in. That's a problem here, isn't it?
Yes.
Because infinity is not a number, it's an idea. But we can still think about what would happen if we let these numbers x get bigger and bigger, grow without bound. So what would happen if I take a huge number and square it? It's going to be huge still, right? Times 3, still huge, right? So that's like infinite, isn't it? That's going to be infinite. Plus, I'm adding twice something that's getting big. That's even bigger, right? So these two terms together are becoming infinitely large. And then I'm subtracting 5. Do you think that really matters to take 5 away from a huge number? No. So would you agree with me that the numerator is approaching infinity?
Yes.
Okay. The denominator, same story. Something huge squared is huge times negative 4. Big but negative, right? Huge negative number. Plus 7. Does plus 7 do much to a huge negative number? No. It's going to get bigger and bigger because that's getting bigger and bigger, and it's just going to stay negative. So would you agree that the bottom is headed towards negative infinity? Okay, so the arrow here is always meant that's what it's headed towards, right? We're not saying it's equal to this. That's what it's tending to. So we have the first time we've seen infinity over infinity in any fashion, right? We've never seen something like this. We've seen 0 over 0, right? But we've not seen infinity over infinity. Now, so what do we do when we see infinity over infinity? Which box are we working with? Top left, top right, bottom left, bottom right? Top left. See, in top left, you know how we have 0 over 0 in here? We also have infinity over infinity in here. Now, don't worry about the minus. Doesn't matter if that minus is there or not. We're still in that top left corner. We have something infinite over something else that's infinite. Doesn't matter that one of them is negative. All right? So what does it say we have to do? Some algebra or some trick. Now, the standard procedure for 0 over 0 was to try and factor, right? And the reason we factored was to try and get something to cancel. You remember that was our main goal? Try and get something to cancel. That is not what we are going to do here. Our goal is not to factor and to try and get something to cancel. And the reason is because, like, let's just say for the sake of demonstration, let's just say that the numerator had a factor of x minus 3. Let's just say it did. Okay, I know it doesn't, but let's say it had that. And let's say the bottom, when we factor it, had x minus 3. We would cancel this, right? And we would have to say to ourselves, as long as x is not 3, right? Well, the difference here is that even if we were to get a factor that matches, we're not plugging a number in, right? I'm not like trying to plug 3 in. I'm trying to plug in a number that's getting bigger and bigger and bigger. It's changing, right? So we can't say, oh, as long as x is not any particular number, because it keeps moving. Does that make sense? So the attack for this, our approach, is completely different. And I think that's one of the biggest mistakes students make, is that they get a problem like this, and then they try and approach it the same way they do 0 over 0. And that's not what we're going to do. So here's the technique. I just have to show it to you first time, okay? Limit x approaches infinity. And just remember this. I'm going to be using this. The limit as x goes to infinity of 1 over x to the n equals 0 if n is basically 1, 2, 3. That's the note I just had up on the board a second ago. As long as we have 1 over x to a power, that power is positive, we are guaranteed that that limit goes to 0, right? Okay, now if we believe that, watch what I'm going to do here. I'm going to look at this expression, and I'm going to identify the highest power of x that appears in the denominator. Okay?
So like a pivot,
What's that?
like the pivot.
Pivot? Is that what you said?
Never mind, I guess
I haven't heard pivot since like linear algebra. That's like a linear algebra term. I'm looking for the highest power of x in the denominator. All right? And then I'm going to do something. Here it comes. I'm going to leave some space in front. I'm going to rewrite the problem. And then I'm going to do this. I'm going to multiply by 1 out in front. I'm going to multiply by 1. But the 1 that I'm going to multiply by is very special. It's going to be 1 over x squared times 1 over x squared. So I got the x squared from the fact that that was x squared. All right? And I'm doing 1 over x squared over 1 over x squared for the following reason. Watch what happens. All right? So you just have to see, like, first time through, like, what happens when you do this. So I'm going to have to distribute that, right? This is going to have to go here, here, and here, and then this one's going to have to go here and here. So let's see what we get on top. Limit x is approaching infinity. And let's see, Trey, where's Trey? What's up, Trey? Doing all right? Okay. Trey, when I do this, multiplication of 1 over x squared times 3x squared, what happens to the x squareds? Go away, right? They cancel out. So all you're left with then is what? The 3. Everyone good? Okay, you got the 3 there. Now when we go from here to here, that's like 2x over x squared. That's what that turns into, right? And then only one of the x's cancels on the bottom. I still have the 2 on top. So that next term next to the 3 will be what? Plus 2 over x. Following or no?
Yes.
We're good? Okay, next, what's the next term? Minus? So we're doing this times this, which is really like 5 over x squared, and nothing cancels, does it? Right? So that's what happens if I distribute 1 over x squared through the top. Emmanuel. Where's Emmanuel? What if I distribute 1 over x squared through the bottom?
Negative 4
Negative 4 plus
7 over x squared.
7 over x squared. We all agree? Okay. Any questions on that? This is just algebra, but you got to make sure you know what you're doing here. Yes?
You have to put the limit as x approaches infinity for each.
Yep, for each one. We never want to get rid of the limit until the time we actually say, okay, now we're going to unleash x and let it go to infinity. Okay, because all we're doing is we're saying, hey, what happens as x goes to well, let me go up here. What happens as x goes to infinity of this expression? We say to ourselves, oh, it's this, and that right there is like 0 over 0. It's bad, okay? Maybe I should have said that. This is bad, just like 0 over 0 is bad. And because of that, what we're going to do is just purely algebra here. We're just going to kind of massage this expression into a new expression. And then now we're going to ask ourselves the same question. So we don't want to lose the limit because this is the ultimate question. What happens as x goes to infinity here? All right? Does that answer your question?
Yeah.
Okay.
I just didn't know if you had to actually put the limit x approaches infinity next to the 3 plus the limited.
No, oh yeah, no, not next to each one. No, because the limit laws allow us to look at a fraction top and bottom separately, and then individually between addition and subtraction. So at the end of the day, I can just leave the limit out here and just do the limits of these individually. But you don't need to write it 6 times. All right, you ready? Let's let x go to infinity now. And we're not going to have the same problems we had before. So I'm no longer writing the limit because now x is going to infinity. What happens to the number 3 as I let x go to infinity? Nothing. There is no x here, right? X has no impact on 3, so that just stays 3. Now, what happens to this? It heads towards 0. Why? Because of this, right? We have fixed over something that's getting big. That's going to get small. It's going to vanish. Now, it never completely goes away, does it? It just gets smaller and smaller and smaller, but we're talking about a limit, so we're asking ourselves, what is it approaching? Well, that right there is approaching 0, so I'm going to say plus 0. And then minus, now what's this one approaching? This term right here. 0 again, because of this. And then on the bottom, what happens? Minus 4, and then plus, this one is approaching 0 also. So you're left with it, when it's all said and done, what? 3 over negative 4, negative 3/4. That's what that's approaching. The numerator wants to get big, the denominator wants to get big. Separately, they want to get huge, right? But that's, as you go out, if you were to graph this function, right? If I were to graph this as a function, it would start to flatten out to negative 3/4. What do we call that in college algebra? As you go out to one side, it starts to like flatten out towards something. We called this thing the what? Horizontal asymptote. It has a horizontal asymptote. And this is what it is. Do you remember in college algebra, you were probably taught this, that if you're trying to find the end behavior of a rational function, like what happens at the left and the right, that you would look at the degree of the numerator and denominator and compare the degree. And if the degrees were the same, you would just do this number divided by that number. Does that ring a bell?
Yes.
Okay, that's how we do it in college algebra. In calculus, this is actually where it all comes from. It comes from the idea that if these are the same powers, right, then when I come through here with 1 over x squared, the only thing left at the end are those two numbers. Those two numbers are the only thing left. So we'll always have that as the answer. Does this make sense? All right, let's do another one. I think I'll do that one next. So you might be asking yourself, well, why can't I just do what I did in college algebra then, right? Why can't I just stick with that? It worked. Limit x goes to infinity of 3x plus 1 over the square root of x squared plus x plus 1. Brian. What's the first thing we always do, Brian? Just check, right? And in this case, we can't plug a number in, but we can still get a feel for what's happening up top. Do you have a feel for what the numerator is headed to, Brian? Positive infinity. Does everyone agree with that? 3x plus 1. As x gets huge, that thing gets huge. That thing's going to become infinitely large, and it's going to be positive, right? Now, same thing, Brian, on the bottom. Positive infinity again, right? Like this is just huge squared plus huge plus 1. Who cares? Plus 1 doesn't do much. Square root of a huge number is still huge, right? So this is infinity over infinity. This is bad. We need to do some algebra. We need to do some sort of trick, right? That's on your page. Doesn't it say here, use algebra trick, right? The trick is like that 1 over x squared over 1 over x squared that we came in with. That's kind of like a trick. It is algebra, but we're pulling a rabbit out of a hat, kind of. All right. So what is the highest power of x you see in the denominator? X squared. Which would make you think that what you need to do is come in with 1 over x squared over 1 over x squared, right? That's not what you need to do, though. Now, if you were in college algebra, you could not use that shortcut in this case. You know the little shortcut that I just showed you where you just grab the two numbers in front? You can't do that because this is not a rational function. In college algebra, when you learn those different cases, how many of you remember the cases, what I'm even talking about? No? I know Brian nodded his head. So no one else learned the cases in college algebra? Okay, then maybe I should just shut up about it. Because I'm trying to persuade you from using it. But if you don't know what I'm talking about, then you're not going to use it anyway, right? So, all right. We look at this. We still identify the highest power of x, which in the denominator, which is x squared. We do still want to come in with a 1 out here. So I'm going to write that down. Limit x is going to approach infinity. And then I'm going to leave myself a little space out there. 3x plus 1. And then root x squared plus x plus 1. All right. The question is, what do I come in with over here and multiply by? 1 over x. Why 1 over x? Because the square root. So if I put 1 over x out here, the whole idea, you're right. The whole idea is to try and make this become, well, basically make this x squared go away. Remember on the last problem we had negative 4x squared down there, right? And the whole idea was to make this thing, this x squared, cancel out. That's the whole goal. So we want to make this x squared cancel out. And we're going to come in with 1 over x, but let me show you why. This is just separate idea from this. Back in college algebra, couldn't we simplify this a little more? Couldn't we look at this as being like x squared times x? And since it was a square root, we could really take this x squared and like pull it out as an x and go x root x. Like these two are the same thing. Does that look familiar to you? Okay, so normally in college algebra, we go from here to here. But what if I gave you this expression and I wanted you to go back to this? Right? What if I did that? Said, hey, take this and go back here. Then you could, if you wanted to, think about it this way. You have to force that x back into the root, right? If you force that x back into the root, what has to happen to it on its way in? It's got to get back to this, right? So what happens to the x as you push it back into the root? It becomes x squared, right? Because this is a square root. If you push the x in, it becomes x squared. If you take the x squared out, it becomes an x. Understand? So what I want is to somehow put something in here where it's going to kill off this x squared, right? So I need to start with something out here, and when it gets pushed in, it needs to become 1 over x squared. So if I use 1 over x out here, and then whatever I do on the bottom, I'm going to do on the top, then as I push that in the root, what's it going to become as it goes in the root? 1 over x squared, right? Does that make sense? What's up? Y'all look befuddled today. Are y'all all right? No? Do you have a question on why it becomes 1 over x squared when it gets pushed in, or?
Yeah, why?
Why? Because of this. So first thing I asked you is, if I write this down, can I write this down? Yes? Okay, then I asked you, going from here to here, have you all seen that? And no one said no, so I kept going. So now's your opportunity to tell me you don't understand that step.
So you have x cubed, and then you make it into x squared times x.
Yes?
You pull out an x,
I pull out an x, right?
and that gives you x
To this.
square root x.
Yes.
Saying if you put that x back in there,
if you're going to go backwards with this, right?
Yeah.
Back up, then you could say that when you push an x in a root, it gets squared on its way in, right? Just like pulling the x squared out, the squared goes away, right? So I was assuming everyone was comfortable from here to here. If you're not comfortable from here to here, then of course going back is not going to make any sense.
What I'm curious about is you have that circle drawn back up to x cubed, so it makes it seem like if you shove it back in, you're going to get x cubed, but
Yeah.
the way I'm seeing it, maybe I'm missing a connection. I'm seeing x squared if you shove it back in.
It will be x squared. It'll be x squared, but there was still an x here already, right? So that x squared times the x would then come together and become x cubed.
So then should it look like x square root x times 1?
X square root of x times 1.
Yeah, because then if you shove the x back in, it would be x squared times x, which would get you x cubed.
I just don't know why you need the 1.
Because x times 1.
Yeah, x times 1 is still x, right? I just don't know why I need a 1.
So there's still the x.
Okay, let me try this a little different. Now let me say something right now. This is all college algebra, and you should all be able to do this, and the fact that you can't is a problem. All right? I'm just going to be very honest with you. But I understand also that in class like this, this is where the problem is. All right? The problem is in the algebra. I can't review something from 1414 for 30 minutes in here. So if I'm going through a lecture and you don't understand a step, you need to let me know, hey, I don't understand that. And then I'm going to try and show you the best I can. And then if I can't clarify it completely, that's where you have to go get clear on it. Yes?
So the way I thought of it, how it came to that, is I knew it was x squared, and then it was the exponent's x, you put an exponent of 1/2. And so when you take that, you put x over 2 over 2. So
It becomes a 1. Yeah. Maybe this might help. Look, do you remember this property from college algebra with roots? That if you have the root of two things being multiplied, that you can split it into two roots, right? And then, well, what is the square root of x squared? X, and then this is just root x, right? So we are at the same place here. So one way to do this is to split it into two and then do this. But really, like as you advance through college algebra, you should not have to write this step. You should just go from here to here. And the understanding is that when you see an x squared in here, it comes out as an x. Okay? So I'm just saying if we go backwards, then you could think of it this way. If you ever need to push something into a root, you can do that so long as you square it on its way in. So like this. If I asked you to take this and push the 4 back in, what would it become? Root 16 times 3, right? The 4 would go in, it would become 16, and then hit the 3. Yes? All right. So back to this. If I'm trying to kill this x squared off, I want to divide it by x squared, then I'm going to have to put 1 over x out here, because when I push 1 over x in, it becomes 1 over x squared. And then it will distribute through and kill off that first one. Does that help a little bit? Okay. All right. So look, y'all have to stop me. I'm not going to be here like, I'm not going to, well, I might throw it in your face a little bit, but I might, I'm going to tell you, you should know this, but at the same time, I want to get you through this class. So if the whole class is struggling with the algebra, then we can take a little time, right? But you have to respond. Don't let me get like so far in the problem that we're all lost. All right, here we go. I'm going to push it in. Limit. X is going to go to infinity. All right, on the top, just distribute through. 3 plus 1 over x. Agree? Just distributing that through. Now, on the bottom, I'm going to push the 1 over x into the root. When I push it in, it becomes 1 over x squared. There it is. Just like that 4 got pushed in and became the 16. Right? And still inside there, I had x squared plus x plus 1. Is that clear to everyone? Yes? Anyone have a question? We're good? Okay, now, pass the 1 over x squared through now. Okay, push it through. So what do we get underneath that root? What's under the root? So what's that? 1? What's that? 1 over x? What's that? 1 over x squared. See, what we're doing by coming in with this 1 is we're trying to use that property to our advantage. Anywhere where we see a fixed number over x, that's going to go to 0. So what we try and do is take this expression that looks like infinity over infinity and rewrite it in a way that when I let x go to infinity, now I'm not going to get infinity over infinity. I'm going to kill off a bunch of terms, right? These 3 terms are all going to head to 0 when I take the limit now. That goes to 0, that goes to 0, that goes to 0. And so now when I apply the limit, what do I get? 3 on top, and then square root of 1, and that's just 3 over 1, that's just 3. So that is headed towards 3. If you were to graph this as a function, and you look out to the right, it's going to head to 3. All right. Derek, where's Derek? Hey Derek, when you see infinity over infinity now, what are you thinking you're going to need to do? Infinity over infinity. Okay, so like look at the denominator, look at the highest power, and then introduce some 1 out front, right? Okay. That's right. That's what we want. Okay, let's look at something different. Limit x goes to infinity of the square root of x squared plus 4 minus x. All right, Luis. First thing, yep, just check it, right? See what happens. So what does all of this head towards? Infinity, right? So this thing is headed towards infinity and then minus what? Infinity. Now we haven't seen that, have we? Infinity minus infinity. 0 over 0 is bad, right? Infinity over infinity is bad. Infinity minus infinity is not 0. Somebody on the test is going to do this, and then they're going to write equals 0, and it's going to be 0 points also, all right? Because infinity minus infinity is still bad. The reason why it's bad is because these two are not the same thing, right? Like if I plug a value of x in right here, it's different than what I get here. So it's like, yes, this is getting big, yes, that's getting big, but who wins? Who wins? One of these guys wins. Or sometimes they compromise and they settle on something. But is infinity minus infinity on here? Yes. It is. Top left. Take a look. Do you see it? So since we have infinity minus infinity here, we're going to use some sort of algebra, some sort of trick. Now I cannot use the method we just used. And the reason why is because in the last 2 problems we had like a rational expression, right? A fraction. So I could do something top and bottom. Here I don't have a rational expression. So there's no top and bottom. So does anyone have kind of a guess as to what I might do?
Add or subtract.
Add or subtract? What would you, do you have an idea of what you might want to add or subtract? Are you thinking add and subtract because, well, it can't be multiplied, so try add and subtract? I'm just trying to figure out where. Not quite sure it's going to get there that way. Think some more about it.
You have to like solve for x or something?
Set it equal to something? No, no. Can't make an equation out of that. What's that? Conjugate. Okay, the conjugate becomes our friend. All right? Anytime we see roots, in problems? Like when we did the limits before, we had 0 over 0 and we saw like roots in there. I said think conjugate. When you see infinity minus infinity, if you see a root, you can start thinking conjugate. All right? Let's see what happens. Now, the weird thing is that if I introduce the conjugate, then I'm going to be doing this. What's the conjugate of that? Square root of x squared plus 4 plus x, right? So if I add that right here, if I say I'm going to multiply by the conjugate plus x, right? I can't just do that. I can't just introduce the conjugate like out of nowhere. I can only multiply by 1. That's all I can ever do. So instead, what I'm going to do is that over itself, which seems ridiculous, but let's try it. Okay, does that seem very strange that I would do that? I introduced the conjugate over itself. So that's really a 1. 1 times anything is still itself. So this is still the same expression. It's just going to look a lot different. Now I'm going to rewrite this as this over 1 just to help me because I'm about to multiply. All right, let's take a look at this numerator. All right, so this times that is what? Just the x squared plus 4. Do I care about the middle terms? No, the middles are going to cancel every time. So all I care now about is the last terms, which are these two. And what is that? Minus x squared. Okay, that's all I'm worried about. Now on the bottom, don't I just have 1 times that conjugate, which is just the conjugate? All right. See that? We got some nice stuff upstairs, don't we? The x squareds are gone. And now we have 4 over something, right? So let's now try real quick. Just let x go to infinity now. And let's see what happens. Let's try it. So what about the top? If x goes to infinity, all we get on top is what? 4, because there's no x's. So we get 4 on top. Now tell me about this. As x goes to infinity, what do you get here? Infinity, right? But then plus infinity, right? Yeah. Not minus. So what happens if I get a huge number and I add another huge number? That's going to get bigger, right? See, we had a problem up here. If I say big number minus big number, you can't tell me the answer because you don't know which is bigger, right? But if I tell you big number plus big number, you can tell me big number, right? So would you agree that the bottom is headed towards infinity? Yeah. Okay. So is this limit giving me a fixed number over something that's infinite? Yeah. Which means it goes to what? 0. So do not take from this. The moral of the story is not that whenever you see infinity minus infinity, you should think 0. That's not the moral of the story. The moral of the story is that you see roots, you come in with the conjugate top and bottom. When you multiply through, it just so happens that this is going to go to 0. All right? I could make the problem not go to 0 if I just tweak some stuff in there.
Professor,
Yes?
will we get some problems where we have to do the other rule?
Yes. So I'm glad you brought that up. It could turn out that what you get here turns out, let's just say maybe it turns out to be 4x over the square root of x squared plus 4 plus x. Maybe that's what you get when you're done with this step. And now you have infinity over infinity, right? Infinity over infinity. And so now you have to come in with that special thing out front on the top and bottom like the previous 2 problems we've done. So an infinity minus infinity problem might turn into infinity over infinity problem. Maybe. It will later for sure. All right. I'm going to try this problem a different way. I'm going to try this problem a different way. With this particular problem, infinity minus infinity, there's kind of like more than one way to skin a cat, so to speak. All right, just see if you agree with me or not with this. I'm a little bit skeptical here. All right. Okay, what What the hell just happened? I took this x squared right here, and I factored it out. If that x squared was able to come out, then it would come out as an x, wouldn't it? But I can't pull an x squared out here because there is no x squared here, right? I can't pull an x squared out of both of these because this one doesn't have an x squared. So here's what I did. I rewrote x squared as I rewrote x squared plus 4 as x squared plus 4x squared over x squared. I know that that's crazy, but that's what it is, right? This is the same as this, right? Now, do they both have an x squared in them? Yes, so I pull an x squared out, and I'm left with 1 plus, I pulled that x squared out, right? So I'm left with 4 over x squared. So you told me that this was x squared plus 4, right? This is equal to this is equal to this. Now that's sitting under a root, that's sitting under a root, that's sitting under a root. So that x squared now can come out as an x. Right? Now, I'm rewriting that as that. Yes? And then next to it I had minus x. Okay, so that is equal to that is equal to that is equal to that. Now look at both of those terms right there. Don't they both have an x in them? So I pulled that x out of both of these. So there it is. There's the x, and then there's that first piece, and then minus 1 because it would have to distribute back. So this algebraically is the same thing, isn't it? Now, why in the world is that good? I mean, like, why would I want to do that? Well, look at this. Let's let x go to infinity. Where does that go? Infinity, right? Times. Now, where does that go as x goes to infinity? What's 4 over x squared headed to? 0, right? Yes? 0? And then I get what? Square root of 1? Minus 1. Right? So what's this headed towards? 0. Shit, that's bad actually. That's bad because look at your formula sheet. Or this little cheat sheet. Do you see 0 times infinity there? It's bad, isn't it? It's bad. So if we ever have this, we haven't had this yet until right now. What I was trying to do was a clever way of like trying to factor out an x to make it just work right out straight away. But when I did it, I just created another bad form. I've got a number getting huge times a number that's getting small. This 0 does not mean 0. It means this is getting smaller, this is getting bigger. Who wins? If I take a big number and multiply by a small number, you don't know. You don't know. It depends on how big that is and how small that is. So this is still indeterminate form. We don't know what it is. So, all right. Well, then the conjugate way looks like it was the better way. All right. All right. Sorry about that, but that was worth seeing the algebra, right?
What do we do in this situation?
Pardon?
What do we do in that situation?
What do we do in this situation? Well, we haven't gotten there yet. Okay, we will be able to deal with this, but it turns out that we're not going to deal with this situation for quite a ways from here. Several weeks from now, we will deal with this. Yeah, stay tuned. All right, let's see. How about something a little more interesting? Like, what about this one? Sine of 1 over x. What happens to that as x goes to infinity? So I'm asking you this. What is the limit as x goes to infinity of sine of 1 over x? That's headed towards, this right here is headed towards 0, isn't it? 1 over x fixed over infinity, that heads to 0. Sine of 0 is 0. So this should be headed towards 0 and there's no more work to be done. A picture of this. There's the picture of sine of 1 over x. And you can see that as you go out to infinity, the function starts to taper down towards 0. So you can do the same idea of x going to infinity with trig functions. You don't have to just be messing with polynomials and rational functions or root functions. Okay, here's one. Here's one. What's the limit as x goes to infinity of sine of x over x? Don't say 1. Why not? Yeah, why not? Why is that not 1? Because x is going to infinity. Remember what we need was sine of junk over junk, right? Which we have. We have sine of junk over junk. But is the junk going to 0? Is that headed to 0? No. Is that headed to 0? No. It's headed to infinity. So this limit is not 1, right? You know, I'm asking you to compare that to the one I said to memorize, which was this one. That one is 1. That one's 1. But this one's not. So what's happening here? So let's try this. Chris? Oh, Jace, sorry. I read it upside down. Jace. This one right here. If you let x go to infinity, can you at least tell me what the bottom's headed towards? The denominator. Infinity, right? Because it's just x. So as x goes to infinity, the bottom goes to infinity. But what about the top? Imagine the sine function, right? We all know what the sine function looks like, right? So it's just doing this, yes? And I'm going out to infinity, and what is that function doing? Is it headed towards one particular number? It's not, right? It's just oscillating up and down, right? So the limit up top does not exist. It's not headed towards anything, is it? Do y'all agree? So this right here as a limit does not exist. Okay, right? And I don't have anything on my sheet that says what to do when you have does not exist over infinity, right? I don't have that on here anywhere. So we have to think about this a different way.
But isn't it sine of x is going to be either negative 1 to 1?
Sine of x will be between either negative 1 to 1. So we would say that that function is actually, do you know the terminology for that? When a function is stuck between two things, what we call that we say that that function is, no? They're stuck between two parallel lines. It kind of has like a ceiling and a floor that it can't go past the ceiling, can't go down below this, right? Does the term bounded make sense? If I say bounded? If I say a function is bounded, does that make sense to you? It's bounded. It can't go above 1 and it can't go below negative 1, right? The sine function is bounded. So is cosine. Cosine's bounded, right? Go back to your little cheat sheet here and look at the bottom. At the very bottom, I have a couple of words down there. What do I say here? Here, meaning in this page, fixed means non-zero and or bounded. Okay? So really, what we have here is this. We have a bounded function over something that's becoming infinite. And therefore, which of these boxes does it fall into? Top left, top right, bottom left, bottom right? Bottom right. Bottom right. Bottom right. Because fixed really means bounded here, right? So what is this limit going to be? It's going to be 0. Its limit is 0. Now maybe I can help illustrate this. All right, maybe I can help illustrate this. Going back to pre-cal. Let's say I define a function a sine of x. What was a? What was the number sitting in front of that? So again, like here's a specific example.